In this video, we're going to figure out the noise temperature of amplifiers. We're going to be doing so in terms of a commonly listed datasheet specification called the noise figure, which requires us to introduce a new metric called signal-to-noise ratio as well. This is our picture of an amplifier, and it's worth noting that the amplifier's noise temperature adds to any noise temperature that's already present in our input signal. That's true of passive networks too, but we need a special formula for amplifiers because the active devices in them create noise in a different way from resistors. Accounting for those noise sources is tricky, but we're going to discover that we can skip that step using a number that shows up in most datasheets called the noise figure. We can evaluate the impact this amplifier has on our signal by defining a measure called the signal-to-noise ratio. The name signal-to-noise ratio is surprisingly expressive. It's literally just the ratio of signal power to noise power. Notice that the signal power is total power, not a density, so we have to assume our system has some bandwidth B in order to calculate our total noise power. I've calculated the SNR of our input signal, which is comprised of everything to the left of the blue dashed line in the schematic, and the SNR of our system's output. The amplifier has clearly reduced our SNR. That leads us to another important metric of performance, the noise factor, which is the ratio of SNR at an amplifier's input to SNR at the output. It measures how much worse an amplifier makes your SNR. The noise figure, which is denoted with the capital letters NF, is the noise factor expressed in dB. We can find a noise factor for our example amplifier with this calculation. This derivation includes a fun step where we express SNR in over SNR out as signal in over signal out times noise out over noise in, which we can do because SNR is just a ratio of powers. Because we're looking at a very generic amplifier model, our final expression for noise factor isn't terribly insightful. Our equations just say that noise factor is equal to 1 plus the ratio of amplifier temperature over input temperature. Sure, that's good, but it's just another kind of trite way of saying that the amplifier adds some noise. However, it is telling that the amplifier's noise is added to 1. The 1 term in that equation comes from the fact that the input temperature gets amplified and sent to the output, which means that the noise factor always has to be greater than 1. Every practical amplifier adds some noise, so it will always make your signal-to-noise ratio worse. We can improve on our expression for noise factor by using it to find the noise temperature of the amplifier's noise. We do this the same way we did with a passive network, by assuming that our input noise is produced by a source resistor which has a temperature T. Substituting the physical temperature T into our expression for noise factor gets us an expression for the antenna temperature. It's equal to noise factor minus 1 times the physical temperature. So in summary, the signal-to-noise ratio is the power of the signal over the power of the noise. The noise factor of a two-port, usually an amplifier, is the SNR of the input over the SNR of the output. Noise figure is the noise factor in decibels. And amplifiers had input referred noise temperature of TA equals NF minus 1 times T.